Yeah, so the last time in the end we'll talk about the formal power series, and I think it will be maybe a little hard. So today we start from the simplest examples of formal power series, and we can maybe understand more carefully what is it. So I remind you the definition. So we can imagine that formal power series is just the sequence of the, so we have the sequence of the numbers a0, a1, a2, a3, and so on, and we can consider them as sum an times t in the nth power. So we have some variable t, and we consider the sequence as formal power series, and we have two operations on the formal power series: the sum of the formal power series and the product. So if we want to find the sum of these two objects, we just consider the sum of an plus bn, and if we want to calculate the product, so it will be the new formal power series Cn times t to the nth power, where Cn is equal to a sum from g0 to n, ag times bn minus g. So maybe we'll start with example. So suppose that we have first formal power series will be 1 plus t squared plus etc. So each coefficient will be equal to 1. And the second one is 1 minus t plus t squared minus t cubed, etc. So it will be alternating sum. So so in the even power we have the coefficient 1, and in the odd power we have coefficient minus 1. So can you find what will be the sum of these two formal power series and the product of these two formal power series? So I think it has the definition, so you can calculate the sum and the product.
Sir, it's only both of us in the class?
Sorry?
It's only Fulo and I in the class?
Yeah. Maybe some of them come later, I don't know. Full, do you know where the others are? Are they coming or not?
I will try to talk to some people.
Yeah, okay. I know, so maybe, I don't know, the last...
connecting, sir.
Okay, so the last time, I don't know, there will be 4 or 5 students, so I don't know, maybe today it will...
Yes, sir, I've already told some that the class is starting.
Yeah, okay, thank you.
Hello, sir.
Hello. I'm asking a question, simplest question about the definition of sum and product of the formal power series. So we have two series f is equal to 1 plus t squared and so on. So the each coefficient is equal to 1. And g of t is 1 minus t plus t squared minus t cubed and so on. So this is alternating sum. And the coefficients are 1 minus 1, 1 minus 1, and so on. And so can we calculate the sum of this formal power series and the product of this formal power series? So maybe I will give another 2 minutes, and maybe someone has the answer. Can we find the sum and the product of these two formal power series?
Sir, it's gonna be infinite, right?
Yeah, of course, yeah. But so you see from the definition that each coefficient depends only. So if you look at the sum, the coefficients depends only the coefficients with the same index from the first two power series. So it will determine correctly. And if you have the product, so if you want to determine the nth coefficient of the product, you just need to know the first n coefficients of each of the row, each of the formal power series. So again, it will be determined correctly. So if you want to calculate the Cn, you need to just summarize the finite number of elements. So we can correctly determine each number. So it's similar to the recurrence relation. So if you have recurrence relation, it's infinite, but you can determine each following element because it depends on the previous elements. So if you know, for example, that you have a Fibonacci sequence, you fix the first two elements and then first two numbers, and then each of the following number is determined correctly, and so it is infinite, but we can calculate each of them. So can you find, for example, the sum? I think the sum is not so much hard.
So sorry, to be equals to I think to be equals to 2 plus the sum from n equals 2 to
even powers.
Yeah, of course. So
so
you see that if you have odd powers, then it will be cancelled because it will have one coefficient one equal to 1, and the other coefficient will be minus 1. So it will be t minus t cubed minus t cubed, and so on. And the even powers are summarized. So we have 2 plus 2t cubed plus 2t in the fourth power, and so on. So we can write this as 2 times 2 times. Sorry. 2 times the even powers. We can write this as 2 times f of t squared, for example. So if we change the variable from t to t squared, then it will be exactly the power series of f of t squared. And what about product?
One.
Why is it so?
because all the other stuff will get cancelled out.
Okay, let's calculate it. So when the first coefficient is equal to 1, because we have 1 times 1, the second coefficient will have 1 times minus 1 plus 1 times 1. It will be 0. The third coefficient will be 1 times t squared, it is 1. 1 times t squared, it is 1. And 1, so it is 0, it is t squared. It is t. And so it is t squared and it is t. So it will be also equal to 1. Yeah? So it will be 1 plus t squared plus something else. So can anyone write the, so which is the next coefficient with non-zero? So which is the next power of t with a non-zero coefficient will be?
4.
Yeah, of course. So you will see that if you have even powers, then we'll have exactly equally numbers of ones and minus ones. So they'll be cancelled and the coefficient will be 0. And if you have odd powers, then we'll have one more 1 than minus 1. So so the answer will be 1 plus 2 squared plus 2 in the fourth power and so on. So it just be phi of t squared. Okay, so if you have, for example, for arbitrary n, we'll have this sum, and it will land on the 1 times 1 if n is odd, and 1 minus 1 times 1 if n is even. So it will be 0 if n is even and 1 if n is odd. Okay, so maybe can give you another example. So suppose we have just the sum of the binomial coefficient. So just usual binomial coefficient will be the first n binomial coefficients of coefficient of n of t in the case power will be n choose k, and the second. So we assume that the other coefficients. So if they in the power greater than k, then the coefficient will be 0. And so here we'll have maybe not this, but and j of t will be is equal to sum from k0 to n choose k times minus t in the k's power. So can we find the product of this two formal power series and the squared of f? Oh, sorry, maybe it is too hard. Maybe, sorry, I need to.
Sir, is f of t plus g of t equals to 0?
Yes, sorry, but I need to. So I need to be more accurately. So I need to. So it is better to look at the. this formal power series. It is similar to the one I wrote, but it will be more easy to calculate. So suppose we have just tk over k factorial from k0 to infinity. And the second one will be -1 in the case power over k factorial times from 0 to infinity. And we want to find what is the product of these two formal power series and what is the square of the first one. And the sum, if you calculate the sum of them, so if you want to calculate the sum of ft plus gt, then it will be just sum of the k from 0 to infinity 2 over k factorial t of in the 2k power, because in the even power will be doubled and the odd powers will be cancelled. So I think that will be this. So again, we can write this. We can write them as the f of 2 of the t squared.
So please, could you show the formula for multiplication again? Up.
You can easily remember it. So you just imagine that you have two infinite brackets and you open them. So what if you open them? Then you have, so for example, here we'll have 1 plus 1 over 2t plus 1 over 3 factorial t squared. Sorry, so this is like, here it will be like 1 plus t over 1 factorial plus t squared over 2 factorial plus t cubed over 3 factorial, and so on. And here we have 1 minus 2 over 1 factorial plus 2 squared over 2 factorial minus t cubed over 3 factorial, and so on. So what if you open the brackets? Then we have 1 times 1. So what's the coefficient before the t? So we have, so if you need to calculate this coefficient, you need to take 1 from the first bracket and minus 1 over 1 factorial from the second bracket. Or you can take 1 over 1 factorial from the first bracket and 1 from the second bracket. So you can just write here that you will have something like this. Okay, so if you want to calculate the coefficient in t squared, then you have, so you can take the coefficient before t squared here and from t0 here, or from t1 over from t here, or you can take the coefficient before t in the 0 power here and before the power 2 in the square here. So we'll have like something like that. Okay, so you just take this coefficient. So if you want to calculate the coefficient before the t in the nth power, you just take the term from the first bracket and find the corresponding term. So if you take the t in the k's power from the first bracket, you will need to take t in the n minus k power in the second bracket. So if when the multiply, then the power will be t in the nth power. And you like consider all these such pairs and then summarize them. And then you will have the coefficient before the product t in the nth power.
So are we supposed to answer f of t into g of t?
Yeah, just find the product of. Do you find the product of them? So we want to
Yeah, yeah.
find. Yeah. So we want to find f of t times g of t. Do you find
Yeah,
it? No.
yeah. Yes, yes. Square of the even terms.
Square of, so you just 1 plus t squared and so on.
No, 1 plus t square, t square by 2 factorial whole square.
T square by 2 factorial and all squared.
Yeah,
So like this.
3 to the power 4. Like 3 to the power 4 by 2 factorial. Because f of t into g of t, f of t is t to the power t square by 2 factorial into t square by 2 factorial.
Yeah, but for example, so you see that. So for example, here we have.
Multiply all the even terms twice. Even terms, all the even powers twice.
Okay.
Yeah.
So something like this. And you just calculate the sum. And I ask you about the product. So multiplication is a little bit harder than just the sum. So the sum is very simple. You just summarize the coefficient and get the answer. And multiplication is harder because you need to calculate the sum of the n elements. So if you want to calculate the coefficient before the t in the nth power, you need to calculate the sum of the n product. But it is not very hard, so we can calculate that. So for example, here we have the first coefficient will be 1, the second coefficient will be 0, because we have here 1 is 1 plus 1. And here we'll have 1 over 2 minus 1 plus 1. Oh, it will be also 0. So for example, in the correct, if the answer is correct, the first will be coefficient will be 1 and the next two will be equal to 0. So all we need to do is to calculate. So if you want to find the n coefficient of the product here, all we need to do is find the following sum. It will be 1 times 1 over n factorial minus 1 over, so I can write this as 1 over 0 factorial. Minus 1 over 1 factorial times 1 of the n minus 1 factorial. So I think, is it so? I need to write this. Oh, so maybe it's correct. If you need to be more correctly, I need to write something like this. So I just put the coefficients from the first form of our series and the second, and then multiply. So I multiply the pairs and then summarize them. So I need to calculate this sum. And I think this is similar to one of the formulas that we proved in the previous lecture, or maybe lecture before that. So I think we know what this is, so we can find the. So
is it the C2n choose n?
Why? So
it looks similar to the time when it was 2n choose n.
So if you look at the denominators, you will see that they have the multiplication of two factorials with the sum equal to n, and it is similar to what formula? So
combination.
Yeah. So it is similar to the binomial coefficient. Yes. So if you only have n factorial, then all these coefficients will be binomial coefficients. So okay, so let's write this as the following way. So we can write this as 1 over n factorial, and here we'll have n over n choose 0 times 1 is 1 in the nth power plus n choose 1 times 1 is 1 to the n minus 1 power and so on. And we have n over n choose n as the last coefficient. Or we can, if you want to, we can rewrite this as 1 over n factorial and n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 and so on. So if you use a symmetry element, so we can summarize not from the 0 but from the n, and so we have the alternating sum of the binomial coefficients. So what is the alternating sum of binomial coefficients is equal to? I think we will prove that this formula in one of the previous lectures.
It equals to 0, sir.
So it equals to 0 if n is greater than 0.
Is not, yeah, if n is not
Yeah,
0.
and it is equal to 1. So, okay, so the answer will be the full. So the answer will be just 1. So all coefficients of this formal power series is equal to 0, except from the first one. So the first one is equal to 1, and all the other coefficients is equal to 0. So we'll just prove that the product of the f of t and g of t is equal to 1. Okay, and what about the f t squared? F squared of t. So if you take the square of this formal power series, so what is changing? So suppose we have like sum of dn times t in the nth power, and n is from 0 to infinity. So if I expand what is dn, what is changing in this formula? So
Alternating sum?
Yeah. So instead of alternating sum, we will have just sum of the coefficients, right? So we'll have something like 1 over n factorial of n choose 0 plus n choose 1 plus etc. plus n choose n. And what is this sum? So
2 raised to power n.
yeah, of course. So it will be 2 power n. So it will be 2 power n over n factorial. And so this will be the sum of the from 0 to infinity to n over n factorial t in the nth power. Or we can just write this as 2t in the nth power over n factorial, or just f of 2t, yes? So we just, the formal power series f, and instead of variable t, we have the variable 2t. And so I think you're familiar with this, because if you look closely at what I wrote from this, so what is this formal power series? So if you know so do you remember which function is written as the sum of the factorials? So 1 over factorials. So if you so maybe we're familiar with this function, which have, so if we take, so it is we can find we can differentiate it infinite times, and if you write the if you can write this as a power series, we will have this function. Do you know? No, what is the function?
Doesn't sound familiar, sir.
No. Okay, but so Okay, so but you're familiar with the Taylor sum, Taylor formula for the function, because you can expand function as a polynomial plus some little function, small function, very small function. And so if you just write the, so what is the, do you know what function has the Taylor formula like 1 over k factorial? No?
I think Rohan knows, sir.
Okay. Okay, but
Yeah, it's
no, you have no idea?
E.
Okay, yeah, of course. So if you take e in the t's power, then if you take the considered Taylor formula for this function, then we have just exactly this power series. Because if you try to differentiate it, that it will have these coefficients like factorials. So it will be equal into t's power, and this will be equal a into minus t power. So it is not very hard to see that if you take the product of these two functions, it will be equal to 1, and we will have the product of square of the first function will be in the power of 2t. So here we have a connection between calculus and combinatorics. So we just prove this formula using the combinatorial identities. And here just you can write the function that has the same answer. Yeah? Do you understand?
Yes, sir.
Yeah. Okay. So the next so the next step is to try to find the so try to consider the inversion of the formal power series. So if we have formal power series, then the inverse of the formal power series is just like the formal power series, such that the product of these two formal power series is equal to 1. So for example, if we have a to the t power, so 18 in the minus 1 power is just a minus t. Does every formal power series has the inverse? It is not true because, for example, if you take if you look at the arbitrary formal power series a of t, then we need to find such formal power series b of t such that at times b of t is equal to 1. So if we expand this equation, then we see that we have the conditions of the coefficients of formal power series b. So the first one should be equal to 1, and the following should be equal to 0. And so maybe this is a system of linear equations. So we have the coefficients of power series A we know, so it's just numbers, and all the coefficients B is variables. So So we have the infinite system, and so maybe it does not have a solution, and so we can find the inverse row of this formal power series. But how can we find it? So we can solve the linear equation. So for example, let me find the inverse of the 1 minus t. Or we can write this as 1 over 1 minus t. So we can just use the usual. So if you have two integer numbers, then we can have we can derive using the following technique. So we just write 1 divided by 1 minus t. So we want to cancel the first coefficient. So first we need to do is to multiply it by 1. So we have here 1 minus t. Okay, so if we calculate it, so 1 minus t will be t. So here we want to cancel t, so we just add t, and here we have t minus t squared. And so we need to cancel this one. Okay, so we have this here to squared, here is t squared, and so on. So if you look closely, you see that so each nice coefficient is equal to 1. So is it true that if I take 1 minus t and multiply it by 1 plus t squared plus etc., then it will be equal to 1? Is it true or no?
Yes, sir.
Yeah. So if you just expand the brackets, you will see that so so if we calculate the coefficient here before the k power, you will see that we have exactly 1 and 1 minus 1, and they will be cancelled except for the first power for if the k is equal to 0. So for example, here we have find the inverse, and it will be 1 plus t squared, and so on. But if we return to this system, then it is one crucial point where it cannot be done. So here we have the first equation. We want to find the b0. So for example, we have arbitrary formal power series a of t, and we want to find the inverse. So first we need to do is to find b0. So b0 should be equal to 1 over a0. So if a0 is equal to 0, we cannot do it. Cannot do it. And so if a equal to 0, a0 is equal to 0, then this equation cannot be solved. So we cannot choose the b0 such that this product is equal to 1. So if a0 is equal to 0, then the formal power series an tn cannot be inverted. So has no inverse. And if it is not true, so if it is not equal to 0, then we have 5b0 as 1 over a0. So if you look at the second equation, then we can find b1 using this coefficient of b0. So this is a1 times b0. So if you want to find b1, then we need to calculate minus a1 times b0 over a0. And here again, in the denominator, we have a0. So if a0 is not equal to 0, then we can find b1, and so on. So if I want to find the formula for the bk, it will be minus sum like ak times b0 plus ak minus 1 times b1, and so on. And again, in the denominator, we will have a0. So again, if a0 is not equal to 0, we can find this coefficient. So we can state that if a0 is not equal to 0, then so we can form a proposition that the formal power series is invertible if and only if a0 is not equal to 0. And so, for example, we can find 1 over 1 minus t. We can find 1 over minus t squared, 1 minus t in the first power, and 1 minus 1 plus t squared, and so on. So if you have arbitrary formal power series with non-zero first coefficient, they are all invertible. And how can we use it? For example, consider, so for each sequence, as in the previous lecture, we can for each sequence we could consider the corresponding formal power series, and so for example, and usually this is denoted by the generation function of the sequence an. So for example, suppose we have Fibonacci numbers, and we consider the corresponding formal power series, the generation function of the Fibonacci numbers. And we want to find the explicit formula, some short formula for this formal power series. So we can do this in two separate ways. First way, so we know that Fn is equal to Fn plus n minus 1 plus Fn minus 2. And we can use this recurrence relation to find the explicit formula for this formal power series. So what we can do, so if you write like 1, so we can write this like f0 plus f1t plus f2t squared, and so on. And if we want to use this recurrence relation, we need to find, so this is f of t. So we need to summarize fn minus fn minus 1 minus fn minus 2, and it will be equal to 0. So if we want to do this, we can just multiply f of t by t, and we will have the formal power series f0 times t plus f1 times t squared plus f2 times t cubed, and so on. And we can consider the ft times t squared. So it will be f0 times t squared, f1 times t cubed, and so on. And if we consider we'll take the first row and just look at the f of t minus f of t times t minus f of t times t squared. So what do we get? So what do we get in the answer? So what if we subtract from the ft, from the first row, the following two rows? What do we get?
So all the terms of f0.
Why f0?
Because f0 doesn't cancel out.
Okay, so let's look at each of the columns. So first column will be f0, and of course it will be f0 will be less because we subtract 0 and 0. Okay, from the second one, we will have like f1 minus f0 times t. Will it be cancelled or no?
No.
Okay. So what is the usual definition of Fibonacci numbers? Do you put f0 equal to 0 or something else? So I just, yeah.
Should we start with 0 or 1?
Yeah, so there is symbol definition. Somebody starts from 1, somebody. So I usually I start from 0. So I think we can start from 0. But this is not much difference because we can shift it generation function to the t, and we will have the something like that. So if you calculate the Fibonacci numbers for this one, so we can find the formula for the Fibonacci numbers for the other one. So it's not that's much hard. So we can just multiply it by t or just forget about t. And you're right that from the second power, this all will be cancelled because we have f2 minus f1 minus f0. Here we'll have f3 minus f2 minus f1 and so on. So this all will be cancelled, and so this will be the answer. So here we'll have just t. And so it will be equal to 0, it will be equal to 1. So we find that if we multiply ft times 1 minus t minus t squared, then we'll have t. So we can find that f of t is equal to t over 1 minus t minus t squared. So we have the short explicit formula for the f of t. Not just some infinite sum of the coefficients, but the exact formula. And so how can we use this formula? We can use the formula into two different ways. First of all, if you know about this type of functions, we can try to separate it into. So we have some fraction, and we can just find. So we can expand it as sum of the simple fractions. So we can just try to find like. So 1 minus t minus t squared is a quadratic equation, and we can find the roots of this polynomial. And if lambda 1 and lambda 2 is the root of this polynomial, then we can find such coefficients a and b that this fraction will be equal to the a over 1 minus lambda 1 t plus b over 1 minus lambda 2 t. And if we do that, so we can prove that f of t can be expanded as a like this one. And we know that 1 over 1 minus t is equal to 1 plus t squared, and so on. And so we know that 1 minus, so if we look can you write the inverse of the 1 minus lambda t? So lambda is just like the coefficient. Can you write what this will be? So what this infinite power series will be?
So it's just the first one with lambda in front of the t's.
Yeah, of course. So it just will be 1 plus lambda t plus lambda t squared and so on. So we just, what do we just change here is just change t over lambda t, so here we can do the same. And so if we do this the same, so we can write this as sum of the this infinite formal power series. And so we just proved the same theorem that I talked with you in the previous lecture. So we just prove that the Fibonacci numbers can be expanded as sum of the geometric progressions, because here we have t in the nth power times a lambda 1 in the nth power plus b lambda 2 in the nth power. So here we have another proof of this equation that Fibonacci numbers can be expand as such sum. So, and again, lambda 1 and lambda 2 is just the roots of characteristic polynomial. So here we have characteristic polynomial, and a and b just some coefficients that we can find solving some linear equations. So again, I remind you that if you have linear recurrence relation, then we can find characteristic polynomial, find this root, and so we can just find the formula for the this linear recurrence relation. And so this is another proof of doing this. So so we can just look at the generation functions, expand this as some of the simple fractions, and then find the coefficients. But here we have another application of this formula. So if you prove that some of the Fibonacci generation sequence is t over 1 minus t minus t squared, then maybe we can find something. So if we have something like this, if we take t equal, for example, 1 over 2, then maybe we can find the sum of this power series. So we can find the sum of the fn times 1 over 2 in the nth power. And the question is, it will be equal to 1 over 2 times over 1 minus 2 minus 2 squared minus 1 over 2 in squared, so it will be 1 over 4. And the answer, so I don't know if you have this theorem in the course of calculus, but maybe you know that. So I can tell that. So there's a theorem. So if we have if we have formal power series, then we can ask the question: is it okay to take t equal to some number? And for some numbers, we can see that it will have. So this power series will converge to some number. So for example, if you take, maybe you know that if I take sum of the t in the nth power, so if I take t equal to 1, then I will have this infinite sum of 1s. It will be tends to infinity. So it will be equal to infinity. And of course, if I have t over 1, then it will be also infinity. But if I have t from less than 1 and greater than 0, then I can. It's just the infinite geometric progression, sum of the elements of geometric progression, and we can find the answer just 1 over 1 minus t. So if I take, so for example, if I have sum from n0 to infinity of 1 over 2 in the nth power, it will be equal to 1 over 1 minus t 1 on t2, so it will be like 2. And also I think you prove it, because if you have 1 plus 1 over 2 plus 1 over 4 plus and so on, this is just the limit of the finite sum, and this is equal to we can write this as 1 minus 2 1 minus 1 minus 2 in the nth power, and this tends to 0 as n ends to the infinity. So the whole formula will be tends to 1 minus 1 over 1 minus 1 over 2 equal to 2. And so we can write the same proof for the each number that less than 1 and greater than 0. And so this is, so some numbers we can put in this formal power series and get the actual number, and some numbers are not working right good in this way. So this is a theorem, and so for each such infinite formal power series, we have some number r called the radius of the convergence. Do we have something like that in the calculus course or no? So you don't have this theorem in the calculus course, yeah? Something like that. So
We know how to find limits, sir.
yeah, okay, but okay. So so is r is equal to 1 over upper limit of square root of n of model n as n tends to infinity. So, yeah. So if you're not familiar with this, it is not so. So it's not bad. So I think this theorem is not very hard. So you can prove it by yourself. So the idea here is that so if you look at the our real number, so there exists some number. So there exists some r. So for each alpha in this interval, we can put alpha. So we can take t equal to alpha and have the answer. So we can find the sum of the infinite sum of an times alpha n. And outside, we cannot do that because it will be so it tends to infinity or some just non-positive numbers. So it will be not true. And so we can use all alphas then lesser than this radius of the convergence or convergence radius. Okay, so so for example, if you take this formula, maybe look a little hard, but I will give you an example. I think we can go to the next concept. So, for example, if you have Fibonacci numbers, we know that we can write them as the sum of the two geometric progressions, where alpha 1 and alpha 2 is the roots of the polynomial 1 minus t squared. Okay, so if we take the square root of n over this element, so we can write this. So I think it is first we can consider that if we take this square root from the first element, then we have just square root of n over model 1 times model of alpha 1. And so this r for the formal power series a alpha 1 n tn. This radius is it will be just equal to 1 over model alpha 1. And if you take this sum, so if I need to calculate this guy, then it is not hard to prove that we look at the alpha 1, alpha 2, and then find what has the maximal model. And so if we have, so if model of alpha 1 is greater than model of alpha 2, then we can divide this all but by alpha 2. So we can write something like or maybe wait, so we'll have like something like 1 over alpha 1, 1 over upper limit of n tends to infinity of the square root of a modulo a plus b times n1 alpha 1 over alpha 2 over alpha 1 in the nth power, and the last guy is tends to 0. So this guy tends to 0, and this guy tends to root of the nth power and root of the a of the modulo a, and it will tends to 1. So it will be all the sum will tends to 1 over modulo alpha 1. And so all we need to do, if you want to find the radius of the convergence of this formal power series, we just need to find these roots of this polynomial. It will be 1, so it will be t squared plus t minus 1 equal to 0, minus 1 plus minus square root of 5 over 2, and the greater one will be minus 1 minus square root of over 2, and so the radius will be equal to 1 over module of, like just like here, or we can rewrite it. So if we just multiply it by square root of 5 minus 1, we'll have here 4, so it will be something like this. Okay, so this is golden ratio is equal to 1, 6, 1, 8, and so on. And so if we want to calculate this sum, we can just take, so S1 over 2 is lesser than square root over 5 minus 1 over 2, then we can just calculate this just using this formula. And so the answer will be equal to 2. So using this generation function, we can find the infinite sums if we have them with the Fibonacci numbers. Okay, do you have any questions? Was it a little too hard, or was it okay?
So honestly, for me, it was a bit too hard, but I think when I rewatch the video, maybe I'll be able to grasp it.
Okay, so we'll have a couple of tasks using this technique to find the infinite power series of some reconciliation. Okay, so so we have like 25 minutes, so maybe. So I want to. So last time I will give you maybe some hard proof of using some strange technique, infinite power series, to find the formula for the Catalan numbers. So we'll prove that. So I remind you that we have Catalan numbers. We can define them into different ways, like the correct position of the two end brackets, for example. And I want to give you some maybe some combinatorial proof. Maybe it will be not very simple, but it's not so hard. But will be another proof of giving the formula for the Catalan numbers. Okay, so first of all, I need to give the useful definition of the Catalan numbers, and it also I give in the previous lecture I give you 4 different definitions for the Catalan numbers, and now we have once more. So I want to prove that if I have, so I live, suppose I live on the grid lattice, and I have point 0, 0, and I have point 2, 2, or in a arbitrary way I will have points 0, 0 and n. And one, I want to look at the ways going from 0, 0 to 2. They're using this grid, but with one. So first question, okay. The first question will be how many routes are there from 0, 0 to 2 if I want to go only to the up and to the right. So for example, so if I want to go only straight right and straight up, so how many ways are there that are getting from 0, 0 to 2, 2, or from 0, 0 to n? Do you know what the answer is? So how many ways
N plus N.
to n? So for example, from 0, 0 to, so here we have, I can write all of them, I think. This one, this one, this one, this one, this one, and this one. I think the total number of the ways from 0, 0 to 2 and 2 will be 6. Can someone give me a formula for the n?
For n comma n?
Or from all possible routes from 0, 0 to n.
Oh.
Okay, so maybe I will write the all possible routes from 0 to 3. Okay. Okay, is it all? Maybe it's something else. Okay, so you don't have the answer yet, no? Ideas maybe? Yeah.
Just a bit more, sir.
But okay, so you
n plus n factorial divide by n factorial into n minus r factorial.
why is it so? And it's just the hypothesis, yeah.
Combination formula.
Yeah, so you can assume that this is the number of some number of combinations, and here we have. So what we going only up and right, so we can expand this all these roots as the sequence of up and right steps. So for example, here we have up and right. Here we have up right. Here we have up right up, and so on. So what is binomial coefficient corresponding to these possible choices of ups and rights? Can somebody answer this? So we have sorry?
Sum of n and n plus n.
So to n.
To n C2.
So we have 2n steps. We need to go n steps up and n steps to the right. So we have 2n steps total.
Yes, 2n C2.
Yeah. So we have 2n steps, and we need to choose the n steps from them that need to be up and n steps to be right. And this is exactly the formula for the 2n over n. So 2n choose n. So we have 2n steps, and we need to choose n steps from them that are going to the up, and the other n steps will be going to the right. So for example, if I have 4 places, I need to choose 2 of them, and they will be going up, and the others will be going to the right. And so here we'll have 4 over 2, which is 2 factorial over 2 factorial 2 factorial, and it will be exactly equal to 6. And for example, here we have 6 factorial over 3 factorial over 3 factorial. It will be 6, 5, 4. So it will be 5 over 4, like 20. And here we have exactly 20 possible roots. Understand here? Yeah.
Yes, sir.
Okay. So if we consider all possible steps, it will be the 2n over n. But if I want to take only the Catalan numbers, I consider all the steps that goes fully over the diagonal. So I write the diagonal here. and take only the ways that goes over the diagonal. So if I do this, I can see that so which roots are going over the diagonal? These two, when we have n equal to 2, and when n equal to 3, that over the diagonal here, 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 and that's all. So we have only 5. So again, we have 2 and then 5 possible choices, and it is not hard to see that Cn is the possible ways going from 0, 0 to n over the diagonal. And so I think it is not hard. It is not very hard to prove it, because you can consider them as opening and closing brackets. So, for example, if we look at the here at the diagonal and consider that, so for each ways up we will write the opening bracket, and for each arrow going to the right we'll have the closing bracket. And so we'll have exactly n opening brackets and closing brackets. So we have n arrows to the up and n arrows to the right, and there will never the closing brackets will be greater than opening brackets, because it will be mean that this root, this way, is under the diagonal. So the condition that this way is over the diagonal means that we'll have the correct placing of the brackets. So, for example, here we have like this one. Okay. So we have one-to-one correspondence between these possible ways and the correct placing of the brackets. Of course, correcting sequence of the brackets. Okay. Do you have any questions? Or is this okay? So all I need to do is to calculate the number of the, so I need to find the formula for the such possible ways. So ways from the 0, 0 to nn that are going over the diagonal. And here is the trick. So we suppose that we have some way that are going over the diagonal, but I need to have the additional construction. So if I just move this diagonal, for example, 1 to the shift it to the down to the 1 point, then this my root will be just fully over the diagonal. And of course, I can look, so I can take the additional construction. So I will have the fully so for example, here I will have the roots from so I can fix the points at A and B, and I want to, so I can find all the possible ways of going to A to B strictly over and I want to correspond. I want to construct a one-to-one correspondence between this one and the some arbitrary root from A to B. So here I can. So for example, let me see. So what can I do? So let me give you an example. Maybe it will help us to see what is happening here. So we have exactly 5 roots over the diagonal here. And what I forgot to, and this one. So I want to do the following. I want to look at this ways and just took the so just took the symmetric over this big diagonal over so let me think for 2 minutes. Yeah, so maybe I need to write. Maybe I need to write another picture. Okay, let me think. So I want to like take the symmetry root. So for example, here, maybe I need to look at this line. So if I symmetrize it, it will be just like this one. Ah, okay, okay. So maybe it will be better. So, okay. So the procedure is the following. I look at this line that lies above the diagonal. Then I take all the roots from after the first intersection for this diagonal and look at this symmetry one. So I will take like, he will have this one, he will have this one, and he'll have like this one. So what is changed is just we take our weight, look at the diagonal above the diagonal, the line above the diagonal, and just look at the first time we intersect with this line, and then just take the symmetry of this root. So we have, like here, we have always going from this point to, oh, something that you see this. Okay, so from this point to this point. So here we'll have from here to here, we'll have like this one, this one, this one, this one, this one, and this one. Also, okay, so maybe this is different size here. Okay. Okay, so maybe I know that I'm a little bit confused. So maybe we will finish for today, and I will explain it in the beginning of the next lecture. So I think you can find. So the idea is that if we construct the right diagonal and symmetrize them, then we'll have all the roots from 0, 0 to other points. And so we can want to prove that the number of Catalan number is corresponding to this polynomial coefficient. Because so do you remember the formula that we proved for the Catalan numbers in the previous lecture? What is the formula for Cn? Do you remember it? So can somebody remind you? So okay, can somebody remind you of the formula that we proved in the previous lecture? Or don't no one remember? So it will be 1 over n plus 1 times 2n over n, and you can prove. So it is not hard to see that. I think that this is just 2n over n minus 2n over n minus 1. Is that right? Because so it is just 2n factorial over n factorial over n factorial minus 2n factorial over n minus 1 factorial times n plus 1 factorial. So we can write here this as 1. So we have n1 n plus 1 over n minus 1 times 2n over n factorial. No. N minus 1 over n plus 1 times n factorial times n plus 1 factorial. No, so we just multiply it by n and divide it by n. So we have like 1 minus n times n plus 1. So all we need to prove that the Catalan number is the subtraction of two binomial coefficients. And I want to, so when I do this trick, all I need, so I want to look at the all possible ways going from here to here. And so we have totally, the idea is that we have 2n over n possible ways going from 0, 0 to n. And we have exactly this number of bad ways that are going fully under the diagonal. And I want to prove it using this technique, and I will think that I will finish this in the next lecture. Okay, so I will remind you all of the definitions, and we will end the proof. Okay.
Okay, sir.
Yeah. Okay. I think that's all for today. So if you have any questions, so ask me. And so we will prove this, and I think we will continue looking at the. So do you consider some partitions in the previous semester or not?
So could you give us an example of what you mean?
Partition. So for example, you have the number n, and now you want to like expand it in the sum of some integer numbers. And so how many ways are possible? How many ways you can take n as a sum of the sum, for example, k summands. It calls the partition. No?
I don't think so, sir.
Okay. Okay. So we will talk at the partitions, I think, into the next lecture. Okay. So thank you.
Okay.
See you next week.
Okay, bye, sir.
Yeah. Okay.
Thank you, sir. Bye.